Welcome to a new tutorial from DIERS International. In this video we will work together through the result pages of a dynamic foot pressure measurement using the DIERS pedoscan system. Capturing the foot rollover motion in dynamics is an absolutely critical component of analyzing gait behavior and function. The course of the COP line in conjunction with the resulting ground direction force is key to understanding functional processes, interactions and compensations. A preface. In many cases, the footprints shown below are referred to as steps, although this actually means the contact faces of the foot with the ground, which are the stance faces. Therefore, if in the following, depending on the context, stance faces or steps are mentioned, then individual footprints are equally meant. Let's not waste any more time now though, and follow me into this video tutorial. As in all other modalities, the Summary Results tab is used for a detailed overview of the recording result. On the left side of the user interface, all recorded stance faces are initially displayed. Depending on the number of recorded steps, the display is larger or smaller. The stance face highlighted in gray indicates the mean step for each side. This mean representative step is determined by observing the pressure distribution in all recorded data and the course of the COP for each recorded step. The imprint that comes closest to the resulting mean value in this observation is determined as this representative. Please note that when less variance is measurable in the recorded print data, this selection becomes more stable. A single strongly deviating step can cause a distortion of the mean values with a usually small number of total steps. If this distorted mean is then closer to the deviated step than to the mean of the remaining steps, then the outlier is selected as a representative, which can possibly be a hindrance in the interpretation of the data. It is best ensuring that you eliminate outliers based on a visible footprint image, the COP line and the contact time during the data analysis. With a trained eye you can even control this during the data acquisition. The graphics and values displayed on the entire results page refer to the footprints highlighted on the left. Also, only these two roll-off processes are initially played via the video control in the blue header bar. You can, of course, also view the remaining stance faces by clicking in the tile of a non-marked impression. You will then notice that the entire rest of the display adjusts to it. Even if the footprints suggest a step sequence here, the individual steps were recorded independently of each other. Only the data for each side is shown here in order in which they were recorded. The parameter area at the top has 4 different measured values. The contact time shows the amount of time between the first and the last contact of the foot with the ground for the selected footprint. The maximum force shows the maximum force value determined, calculated on the area of 1 square centimeter. This value can be clearly assigned, which means not in multiple places at the same time. The foot segment in which the maximum force value was found is also indicated. The surface indicates the area with which the foot touched the ground. It does not matter whether all pressure signals were recorded simultaneously or independently in time. The foot rotation indicates the direction of rotation of the anatomical longitudinal axis with respect to the gait direction. This quantification is performed exclusively on the basis of the mean steps. It is thus the only parameter that does not change when another step is selected on the left. The reason for this is the difficult automatic determination of this parameter due to the dynamics of the foot rollover. The rotation value given here is therefore completely dependent on the correct arrangement of the longitudinal axis of the foot between the center of the heel and the interdigital space 2 and 3 in the second step of data processing. The total force is a representation of the measured ground direction force of a rollover. In these diagrams you can see the force curves of the selected steps in red for left and blue for right. The light gray area behind represents the standard deviation for all recorded steps. The dark gray graph is the mean force curve for the respective data set. A brief explanation of the recording of force via a pressure measuring platform. Technically speaking, a pressure plate also records force. Contrary to the function of the sensors in a force plate, however, these sensors are only able to register vertically running force vectors. On the other hand, this design and mode of operation allows a disproportionately higher sensor density, so that this vertical force can be recorded over the entire sole of the foot and thus become visible as a pressure or vertical force distribution. So, if you were to compare the ground reaction force curves of a force plate they would be slightly higher because horizontal forces are quantified in addition to the vertical force. However, the characteristic shape of a force curve remains unaffected. The gait phases of a stance phase can be read relatively easily from a force curve. The curve starts with a small peak, which represents the initial contact. Since the actual load transfer does not begin until after this point, the peak initially decreases again a little. This is due to the initiation of the physiological heel eversion and the soft heel cushion that initially transmits the force. From this brief moment, however, the force curve begins to rise in line with the load transfer. In the rising section, the body is in bipedal support. Increasing load creates torques in the joints that are controlled primarily by eccentric muscle activity of dorsiflexors as well as knee and hip extensors in the sagittal, hip abductors in the frontal, and knee external rotators in the transversal. This is the central functional task in the so-called loading response, the phase we are currently in. The moment of maximum force is also the moment of maximum eccentric demands on the structures mentioned. A multitude of gait deviations become visible here. At the same time, this moment is the end of the loading response and the transition to the single support phase, which begins with the well-known mid-stance. In mid-stance, the ground reaction force decreases. This is made possible by a large support phase, since the foot has already fully lowered to the ground and the forward momentum automatically tilts the tibia ventrally. The muscular input required for this is negligible, hence the decrease in force values. Through the tibial forward movement, the heel pressure slowly begins to decrease and transitions into concentric activation of the plantar flexors. This is the change from mid to terminal stance and is equivalent to the moment when the bottom of the force curve has been passed. From this moment, the force curve experiences its second increase caused by the increasing contraction of the plantar flexors, which reaches its concentric maximum at the end of the phase with the second maximum of the force curve. Did you know that at this point the force development of the plantar flexors increases to a level of up to 85% of their maximum voluntary contractile capacity? This is also the cornerstone for a wide range of gait deviations, since in today's sedentary era we often see the tendency for the retrotibial muscles to weaken. At the time of maximum force, the contralateral foot hits the ground, the single support phase is ended and the pre-swing begins. Here, load is successively transferred to the contralateral foot and the force curve decreases completely at the end of the contralateral loading response. On the right side of the screen you can see the pressure distribution image of both selected feet and the COP line drawn in it. This view offers you various visualization options. Choose, for example, whether you would like to continue to have the pressure data displayed in interpolated form or perhaps rather as a representation of the actually loaded sensors. By default, the foot pressure is displayed using the maximum pressure values measured on a sensor during the contact phase. This allows a time-independent view of the maximum loads underneath the sole of the foot. If you switch to the display of the average pressure instead, the average load of the individual sensors is now set in relation to each other. Here, the temporal context in which the pressure is generated takes on a much greater significance, which comes to the forefront completely via the selection of the contact time. The color scaling is now no longer based on the concrete pressure values, but differentiates exclusively on the basis of how long the individual sensors were loaded during the contact phase. A mild plantar flexor contracture would possibly be better visualized by the contact time than via pressure-based representations. The force time integral is probably the most neutral accounting between absorbed pressure and the time of its generation. Mathematically, the rolling motion can be divided into a force curve for each sensor hit. This force curve extends from the beginning of a sensor load to the end and thus encloses an area below it, the so-called integral. If the integral of one sensor is larger than that of another, it is registered as more intensively loaded. In this way, it is color-matched. For many users, this form of visualization is the most intuitive due to the aforementioned neutral force time calculation. The pressure images are color-scaled. As the pressure increases, the model is first displayed in dark blue, then light blue, dark green, light green, yellow, orange, and red. It is thus easy to see where the foot is exposed to high peak loads. If the color scale displayed does not allow you to differentiate sufficiently, simply drag the slider under the pressure images further to the left. In this way, you reduce the display threshold so that less stressed foot zones are also highlighted somewhat better. However, you also tighten the borders between the color gradations in this way. The center of pressure line will be discussed later in this video. Building on the visualization of the foot zone contact time in the Summary Results tab, here is a slightly more detailed look. In diagram 3, the foot zones are divided into the following areas. Medial heel in light green, and lateral heel in dark purple. Midfoot in green. For the metatarsal zones, yellow for M1, light blue for M2, pink for M3, brown for M4, and red for M5. In the toe area, the hallux is blue and the remaining toes are purple. The display consists of a reference to the automatically determined mean steps. On the side edges, you can see the duration with which the respective foot zones have measurably touched the ground. At the top center, you can see the foot zone segmentation on which the display and the parameter calculation is based. Please note that the accuracy of the determination of the foot zones from a dynamic process turns out to be relatively difficult and depends to a large extent on the gait behavior of the patient. For this reason, you have the option in the data processing to refine the segmentation based on your expertise. Your adjustments will then be fully incorporated into this results display. The graphs shown below represent the development of the force under the foot segments over time. The color coding corresponds to the already mentioned segments. Even if this Results tab does not have its own video control, an index bar is offered in these graphs which marks the moment that was selected in a video control of the first Results tab. In addition, the segmental force values are displayed in the percentage of the segmental range related to the total contact time. The basic page structure is the same as the previous result page for the foot zone contact times. However, the focus on this page is on the actual vertical forces absorbed. These force developments in a temporal context once again provide a very detailed insight into segmental involvement in weight transfer and forward movement. In the area of the metatarsal section, for example, it can be expected that the force application already begins in the loading response and describes a transfer from lateral to medial. Following this idea, the chronological sequence would first show the red, then the brown, the pink, the light blue, and then the yellow force curve being loaded one after the other. However, a mildly everted foot would already confuse this sequence. Here we would clearly see how the first segmental force increase does not start on meter 4 or 5, but on meter 3, M2, or even M1. This view is a slightly larger representation of the matrices from the Summary Results tab. More visualization options exist here. Choose whether you want the pressure data to continue to be displayed in interpolated form, or perhaps you would prefer to see it as a representation of the sensors that are actually loaded. You can also view the pressure data of the index matrix in 3D instead of two-dimensionally. This is used to separate pressure areas not only in terms of color, but also spatially. To the right, you can set the data to your preferred default view. However, you can also select an individual view by moving the mouse pointer into the index matrix and holding down the left mouse button. Drag the mouse up or down. The pressure image rotates vertically around the horizontal axis. If you drag the mouse sideways, the image rotates around the vertical axis. If, on the other hand, you hold down the Alt key and drag the mouse sideways, the image rotates around the center axis. So far, this view corresponds to the functionality of the Result tab of the same name in static pedoscan. But what is the real added value of this page? The slowed down but continuous playback of the rolling motion via the play control in conjunction with the COP line shows you exactly how the body weight is carried over the ground, which foot zones bear the main load and which zones are relieved. How is the COP line to be understood? Let's think back to the static foot pressure measurement. The center of pressure combines the pressure distribution of a foot under one point. This is therefore the point towards which the body weight is tapering. In a dynamic situation, this is of course much more varied than resulting from pure postural sway. The COP line therefore shows a course over time as well as its position in the overall pressure pattern. In the optimum case, the COP line runs as follows. In initial contact, the foot hits the ground in a slight inversion due to the activity of the dorsiflexors. The COP therefore arises slightly lateral to the center of the heel. However, due to the load-induced initiation of the physiological eversion movement of the heel, the COP immediately tilts medially to the center of the heel. The pressure pattern shows a pressure development originating from the center of the heel. In loading response, the COP line takes on a recognizable course in the direction of M3. The end of this phase is reached as soon as the front edge of the heel is reached. The expanding pressure in the heel area initially increases, but then decreases again somewhat as the forefoot is lowered. In mid-stance, the COP maintains the direction taken and runs in a straight line towards the third toe in the direction of the forefoot. According to the lower ground reaction force, the longitudinal arch is clearly visible as a pressure zone, but does not show any pressure peaks. In the later course of mid-stance, a slightly expanding pressure peak appears at the lateral forefoot, which is oriented medially in its development. Having reached approximately the anterior third of the metatarsus, the COP begins to represent the terminal stance. In this phase, the COP line passes into the metatarsal region, and the COP transfers the pressure analogously from lateral to medial in the direction of the hallux. The maximum pressure moves across the entire width of the anterior transverse arch from lateral to medial. In pre-swing, the COP is then transferred from the more medial metatarsal bones to the hallux. The last measurable contact is generated by this. Many foot dysfunctions that are not yet apparent in a static situation can be detected much more precisely via dynamic loading, since individual zones may be loaded more selectively over time. The last point mentioned as an example. If you can see toes in addition to the hallux at the last moment of pressure release, this can indicate relief of the hallux, for example in case of a hallux rigidus. The red expanding pressure berry of the lower longitudinal arch clearly appears in mid-stance. That's the moment when the foot is completely lowered and the body's center of gravity is guided over this very midfoot. A static image can only make this measurable in a much more pronounced form, since the pressure can be distributed over a larger support surface here. For this reason, a splay foot will also always be more impressive dynamically. At the moment when the body's center of gravity moves toward the forefoot, and the pressure in the metatarsal region increases, the anterior transverse arch should fulfill a bridging function that guides the COP from lateral to medial. A splay foot shows here either a much larger pressure region, which does not show dynamics following the COP, or separate pressure zones below the metatarsal heads. In the latter case, the metatarsal heads stand out separately but simultaneously or appear as pressure berries in rapidly succession. A flat foot appears with an evenly distributed pressure pattern and a clearly widened midfoot. The COP line runs relatively straight and possibly somewhat faster over the midfoot. But now let's move on to the differential diagnosis of pes cavus, which is a high-arched foot, and a pes valgus, which is an everted foot. This has already been addressed in the tutorial on static foot pressure measurement, with reference to the difficult feasibility, as often too few clues are visible in the static context. So how do the two foot types differ in dynamics? In many cases, the functionally characterized pes valgus shows a completely inconspicuous heel composition. As expected, the COP line runs centrally towards M3 after initial loading of the lateral heel. The excessive eversion then occurs only at the moment when the line leaves the area of the heel and passes into the midfoot. If we recall the course of the ground reaction force, this coincides with the first force maximum and the accompanying end of the loading response. From this point, the COP line bends medially, resulting in a shift of pressure development in the forefoot also medially. Increased diversion at this stage has an essential compensatory function in mitigating the eccentric stress on the hip abductors at this stage, as it ensures that the transfer point of the ground reaction force is positioned closer under the body's center of gravity through medialization. The high-arched foot, on the other hand, maintains a regular COP course. Over the missing pressure pattern of the midfoot, the COP continues in the direction of the third metatarsal without a visible bend toward the medial side. The pressure development on the forefoot also runs regularly from lateral to medial. A distinction should be possible without further ado, taking into account the points mentioned above. Well, this concludes this tutorial video. I hope you were able to learn a few new things again and see the presented measuring system with new eyes. If you enjoyed this tutorial, we'd love for you to tune in to the other training videos as well. So keep at it and join us in our next tutorial video.